Let's look at an example. In this reaction, we're taking an aldehyde. It's ethanal. Ethanal is CH3CHO. Ethanal breaks down into methane, CH4, and carbon monoxide. And so let's say we do a study of this reaction, and we're studying the amount of ethanal that we start with, and then we're figuring out the rate of disappearance of ethanal. So let's talk about this. We're going to do multiple experiments. This is the amount of the reactant ethanal we're starting with. And over here, this number, this is the rate, all right? It's moles per liter per second, or molarity per second. So that's the speed. So notice here that at 0.10 moles per liter, our rate, the disappearance thing over there, 0.020 molarity per second. Well, in our second experiment, we double the ethanal. We go from 0.10 to 0.20, all right? So notice that going from 0.10 to 0.20, we're doubling the ethanal, all right? i.e. 0.20 divided by 0.10 is 2, all right? When I said earlier about doubling, there was a reason for that, because here we're doubling the ethanal. Now, look at the difference in the rates on the right side. 0.081 is quite a bit different than 0.020. If ethanal would have been a first-order reactant, then we would have went from 0.020 to 0.040. Doubling in a first order makes a doubling of the reaction rate. And if the ethanal would have been a zero-order reactant, then doubling ethanal, we would have still had a number for the disappearance, which was about 0.020. Wouldn't have changed at all. However, in this case, doubling ethanal made quite a different change in the rate. It went from about 0.08 to 0.02. That's a factor of 4. So the difference here, 2, the difference between these two, about 4. And remember that the ethanal right here, it's got a factor. We're trying to see what this factor is. 2 to the x equals 4. What do you think x is going to be? And remember, in our classes, x is only going to be 0, 1, or 2. If you said x is probably going to be 2, pat yourself on the back. We'll see why to get that. If you didn't get 2, hang tight here a little bit. Let me keep going. All right, so this scientist decided to get some more data. So they got experiment number 3, where they went to 0.30 moles per liter. The rate now 0.182, so you can see it's going up even more. And finally, experiment number 4, they had 0.40. They went up to 0.318 moles per liter. Now, what we're trying to do here is we want to find the rate law. And the first step here is to do a set of experiments like we've just done. You're changing the concentration of one of the reactants, in this case, the only reactant, and we're going to use differences between two of the trials and compare them to the rate to see what those values of x is. So when I did the 2 to the x equals 4, again, the 2 part came from 0.20 divided by 0.10, and the 4 is about approximately equal to 0.081 divided by 0.020. So in this problem that we're looking at right here, we're trying to figure out the components of rate equals K times the one reactant, ethanal, CH3CHO, to the x. And when you want to solve for a rate law, the first thing you've got to figure out is the x, that order of reactant. So you can compare any two trials where the ethanol changes, but the other reactants, or if there are any, stay the same. Now in this reaction, it's pretty easy. We have only one reactant. So let's compare number 2 and number 1, because we're doubling the ethanol, and we're going to look at the change in the concentration relative to the change of the reaction rate. If you look here at this part, rate equals K times ethanol to the x. So for trial number 2, the rate is the 0.081. That equals K times the concentration of ethanol in number 2, which was 0.20 to the x. We're going to divide that by rate 1. So rate 1 was 0.020 on the bottom, and that equals on the bottom K times the ethanol, 0.10 to the X. Now, the K's will cancel out here, all right? K's cancel out. So you have 0.081 divided by 0.020, which is 4.1. I said it was about 4 earlier. 4.1 is even better. And then in the exponent world, 0.20 to the X divided by 0.10 to the X, you can combine that into one big problem to the X. So 0.2 divided by 0.1 is 2 to the X. So 2.0 to the X equals 4.1. And remember, X can only be 0, 1, or 2. So let's go through what would happen if X was 0 first. Well, if X was 0, anything to the 0 power is 1. So if you had there 2.0 equals 1 for rate 2 over rate 1, we'd say that X was 0. But obviously, the rate 2 over rate 1 is not 1, so this is not a zero-order reactant. If X was 1, then 2 to the 1 is 2. So if rate 2 over rate 1 was about 2.0, then we'd say X was a first-order reactant. It's not a first-order reactant. So let's try if X equals 2. 2.0 to the second power would be 4. Hey, that's looking pretty close there to 4.1. So X equals 2. This is a second-order reactant. But wait a minute, Dr. Russell, I don't like that way of thinking about things. That's totally cool. I kind of a hand grenade way, it works, but it sometimes feels a little bit cheesy. In the kinetics labs we're going to do, you can also use logarithms to get a better value of X. Now, 4.1 equals 2.0 to the X. In logarithms, you can break that down, add a log, and it can be natural log or base 10 log, but I use base 10. So log 4.1 equals log 2.0 to the X. And one of the cool things about using logarithms is you can rewrite log 2.0 to the X as X log 2.0. So this is a way to get the exponent by itself. So log 4.1 equals X log 2.0. You can solve for X. X equals log 4.1 divided by log 2.0. X comes out to be 2. So either way, either by thinking about what happens when X is 0, 1, and 2, which is what I did first, or if you want, you can use logarithms, you should find here that the X value is 2. So we would refer here to ethanol, the CH3CHO, as a second-order reactant, all right? We'll talk about more what it means to be second-order, but for right now, just realize finding that little exponent, that order of the reaction, super important. And this is what you do. You have to do this through experiment, all right? You can't do this theoretically by any ways known. You have to take several trials and compare them, like we did in this example, to find the order X. Here's a reaction. 2NO plus 2H2 goes to N2 and 2 waters. And it says that the reaction above is second order in NO and third order overall. And it says then what's the rate law for this reaction? Okay, so what we're trying to do here is find rate equals K times NO to the X and H2 to the Y. And it says there that the reaction is second order in NO. So the NO to the X, that means the little x, the superscript up and to the right of NO, will be 2. Now, it says also that it's third order overall. So it's second order in NO, and the order of NO plus the order of H2 equals 3. That's what the third order overall is. So it probably, you can see then, third order overall minus the second order thing, X, the hydrogen value is going to be 1. H2 is a first order reactant. So for this reaction, you would write rate equals K times NO to the second power times H2 to the first power, or just H2 by itself. Notice that NO was a second order reactant, and that too just happen to be the same as the order with respect to NO. On the other hand, the H2 is a second order reactant, or it's stoichiometry of 2 in the reaction, but the overall reaction here means that H2 is a first order reaction. So I put this problem up because first of all, it gives me a chance to talk about overall rate orders, which is kind of interesting. But also I want to point out that the stoichiometries of the reactants and products are often going to be different than the rate orders. So NO here happened to be a rate order of 2, but you can see here that hydrogen is not a rate order of 2, i.e. answer D is not correct. In this problem, we had to use the idea that the overall order is 2, so that means the order here, the answer here is going to be C. So the stoichiometries are not necessarily the same as the reaction orders, and that's pretty important. In the last problem, we saw that the ethanal is a second order reaction. So far then we'd write rate equals K times the ethanol to the second power. So the questions then say, all right, here the rate goes up by blank when the initial concentration doubles. Well, if the concentration doubles, that means the ethanol, the part in the square bracket, doubles. 2 squared, the rate would go up by 4 times. So this reaction, because there's a little 2 right there, that means this reaction is second order. Once you have the order of a reaction, you can go back and solve for the last part, the rate constant K. And rate constant K has some really good uses we're going to see. You can use any of the experiments in the previous slide's data. All right, you could use experiment 1, 2, 3, or 4. In this example, I used experiment number 3, and the rate in experiment 3 was 0.182, and that equals K, which we don't know yet. And experiment 3, the concentration of ethanol was 0.30, and we know now that ethanol is a second order reactant. So 0.30 squared. So K here would be 0.182 divided by 0.3 squared. K comes out to be 2.0. You don't have to report any units for K. The units of K are all over the place, and people honestly don't usually report them. But if you are curious about units, in this case it would be liters per mole seconds. But again, don't lose any sleep over that. Anyway, once you have K, you can calculate the rates of other values of ethanol as long as you don't change the temperature. If you change the temperature, you have to recalculate K. We'll talk about those kind of things later. We need to know what the concentration of a reactant is as a function of time. And a heck of a lot more reactions in the actual world are first order. All radioactive reactions, which we're going to look at a lot in the next chapter, all of them are first order. All biology reactions that are known anyway are first order. And a lot of chemistry reactions are first order as well. So this is one of those times, I always hate to say this, but if you have to guess first order, because there's a lot more first order reactions than anything else. If you have a first order reaction, all right, then rate equals K times the reactant R to the first power. And remembering that rate is the negative, because you have to keep them negative because they're reactants, rates equal negative the change in the reactant concentration over change of time. So instead of writing rate equals K times the concentration of R to the first power, we rewrote here the rate part for what it actually is. It's negative the change of concentration over the change of time. And of course, because the first order reactant, something to the first power, people usually just ignore it. This is actually kind of helpful, believe it or not. If you integrate this, and this is where calculus comes in, and you don't need to integrate anything in Chem 222 or 223, but if you have seen calculus, or if you will be seeing calculus, it's not too hard to do. Anyway, you integrate this thing, you end up with this expression right here. And this expression with the natural logs, which comes from integration, natural log R over R0 equals minus KT. Now, a couple of things. ln is the natural log. It's not the base 10 log, log. So if you're going to do these problems, make sure you use the ln button and not log. The second thing, R0 there means initial amount of R. So that's like how much R you start with. And then the rest of it, on the top there, you've got just R. That's the amount of R at time little t. So sometimes in some texts, you'll see like a little t right there. It's the amount of R left at time t, and that equals the negative rate constant. K is the rate constant here. But this equation is actually super helpful for scientists. It's called the integrated first order rate law. And if you know the reaction is a first order reactant, and almost everything in chemistry is, basically everything in biology and nuclear radiation is, then, oh my gosh, you can find out so many cool things. And so we're going to use this expression a lot, all right? And again, it's natural log R over R0 equals minus KT. And there's a lot of neat things you can do with it, and I'll show you some of those here coming up. Sucrose is a type of sugar, and like a lot of sugars, it will break down over time. And the rate of disappearance of sucrose, because it's a biological function, it's first order, so you can write rate equals K times sucrose concentration to the first power, or just rate equals K times sucrose. And someone has already calculated the value of the rate constant K to be 0.21 inverse hours. If you see that inverse hours, you just realize that equals 1 over hours. All right, it's the same thing. Hours negative 1 takes maybe a little less time to write than 1 over hours. But anyway, I digress. So let's say that you have a sucrose concentration of 0.010 moles per liter, and you want to know how long it's going to take to drop to 90% of the initial value. So how long is it going to take to go to 0.0010 molar? Well, if it's fast, you don't mind waiting around. But if this is slow, you might want to go do other things, all right? You might want to go study journal articles in the library, or go see a movie, or whatever kind of things you might want to do. This is actually a way that you can figure this stuff out using that first order integrated rate law. There's all the data at the top. We're going to use that first order integrated rate law, which was natural log R over R0 equals minus KT. Now, the amount we started with, R0, 0.010 molar, and that goes in the bottom. The amount we have left, i.e. R at time t, 0.0010 molar. So R over R0, how much we have left divided by how much we started with. And that equals minus KT. So K is that 0.21 inverse hours, and we basically want to solve for T, how long it's going to take. Now, a couple of things. When you're doing the natural log R over R0, R and R0 have to be the same kind of units. They have to cancel out. So you have to convert one into the other if you don't have the same kind of unit. Here we have 2 molarities, so it's no problem. The other thing is that K and T are both going to be positive numbers, okay, all the time. No negative Ks, no negative Ts, at least not in this class anyway. So if you do end up with something negative, it probably means you forgot that little minus in the minus KT. And then finally, the units of K and T must be the same kind of unit. Now, K will be inverse time, like here it's inverse hours. And in this problem, the T, the time elapsed, is going to be regular hours. So you wouldn't want to use like inverse hours and seconds, all right? You'd have to convert seconds into hours, or inverse hours into inverse seconds. They have to be the same kind of unit. But anyway, this is a good time to do this problem on your own and see if you get the right answer. Make sure that you use the natural log and not the base 10 log log. So natural log 0.0010 divided by 0.010, that comes out to be natural log of 0.100. And if you put that in your calculator, that comes out to be minus 2.3. So natural log 0.0010 divided by 0.010, negative 2.3. And that equals negative KT K is 0.21. Time is what we're solving for here. So time is going to equal negative 2.3 divided by negative 0.21. The negatives will cancel. We'll have a positive value, which I said earlier was so important, etc., etc. This value here comes down to be 11 hours. So your sucrose will go down to 90% in 11 hours. I would come back within, say, 9-10 hours just to make sure you're still on target. You never can tell about science, always some flexibility, but this is a way to estimate pretty well how long reactions are going to take. For the reaction, A going to B, the disappearance of A is first order when K equals 0.030 inverse minutes. If we begin with a concentration of A of 0.36 moles per liter, what will the concentration of A be after 46 minutes? Okay, so let's think about what we've got here. So first of all, this is the integrated first order rate law. Natural log R over R0 equals minus KT. Okay, so R0 is the 0.36 moles per liter number. We don't know R, how much is going to be left after 46 minutes, but we do know that K, 0.030 inverse minutes, and the time elapsed 46 minutes. The times are in the same kind of unit, inverse minutes and minutes, so that's no problem. Remembering that there's a negative sign in there, the concentration will come out to be a positive number. Now, it will not be 0. All right, answer E. That doesn't make any sense, but the other ones, honestly, you just kind of have to put into the math problem and figure out what it is. So when I did this, I got a value of 0.091 moles per liter. And you can see there what exactly I did. I started off by taking natural log R over R0 equals minus KT. And like we talked about, R0, 0.36, K, 0.030, time 46. And at that point, you just got to kind of get rid of everything. Now, if you haven't done a lot with logarithms, you've got to get rid of the logarithms. This little E thing right here, E is called the anti-natural log. And you've got to get rid of the natural log there in order to make sense of all this. So we're going to take the anti-natural log of both sides. Usually on the calculator, you'll have an lnx button or something like that. And then usually second function ln says a little ex, e to the x. And that's the anti-natural log. You don't have to worry about the math part of it. Just plug and chug this stuff. So what you want to realize is that e raised to the natural log, these two will cancel each other out. But on the other side, you do have to go e power negative 0.030 times 4 times 46. If you get an answer of 0.252 to 3 sig figs, you've done it right, all right? If you haven't gotten that answer, please take a screenshot of it or a picture with your phone, whatever, send it to me. Let me see if I can help you out with this problem, because this stuff it's not hard, it's all plug and chug, but it can be a little bit weird. Anyway, the e and the natural log on the left cancel, so you have r over 0.36 equals 0.252, and then r itself is just 0.36 times 0.252. That's where the 0.091 number came from. So this is the kind of problem you'll see in this section. Nothing you can't handle, but make sure you can do this problem before you move on. The integrated rate law suggests a way to tell if the reaction is first order based solely on experiment. So here's another reaction. Dinitrogen pentaoxide is kind of unstable. It breaks down into NO2 and O2. And the rate here equals K times N2O5. So this is a first order reaction. All right, somebody has figured that out. Well, let's say we do this reaction and we're taking the concentrations of N2O5 at different times. So 0, 1, 2, and 5, there's the concentrations of N2O5. And you can see it's decreasing because it's a reactant, it's going down. Now, for reasons that'll be clear on the next page, I'm taking the natural log of those numbers. So natural log of 1 is 0, natural log 0.705 is negative 0.35, etc., etc. I'll show you why I'm doing that, but that's something we're going to do in this section. So if you do need natural log of those numbers, just natural log 0.173, that comes out to be negative 1.75, etc., etc. If you plot the concentration of N2O5 versus time, it doesn't come out to be very straight. And hopefully you can kind of see here that the N2O5 is kind of curving. And scientists really like to have straight lines because straight lines mean you can do like equations, all right? Curved lines, you could do equations too, but you need to do powers or exponential analysis, stuff like that. However, if you plot the natural log of the concentration versus time, you get a really nice straight line. So notice here that just plotting concentration N2O5 versus time really didn't do that much. But natural log N2O5 versus time, we get a nice straight line. And if you think about our discussion so far, this may not seem totally out of control because natural log R over R0 equals minus KT can be broken down. Now, in the logarithm world, natural log R over R0 you can rewrite as natural log R minus natural log R0. So to get to the expression right here, we took the natural log R over R0, which is natural log N2O5 divided by natural log N2O50, and we first wrote it as natural log R minus natural log R0. We then added natural log R0 to both sides, and lo and behold, natural log N2O5 equals negative KT plus natural log N2O5 at 0. And you're like, Russell, you've lost it. This isn't any easier than it was before. Oh, yes, it is. Because you have the equation for a straight line. Your y-axis is this whole thing right here, the natural log of N2O5. The x-axis is the time. So the slope is going to be equal to negative k. Your slope will be negative. You take the positive version of that negative slope, that's going to be your k. But also really cool, the y-intercept is going to be related to the amount of reactant you started with. So if you do a linear regression on this data, linear regressions automatically generate slopes and y-intercepts for you. Slope equals negative k, so negative slope equals k. This is the coolest way to find rate constants, hands down. And also, we're going to see sometimes it's difficult to figure out the amount of reactant you started with. Well, if you do natural log concentration versus time, y-intercept equals natural log N2O5. So you take the anti-log of both sides, that's going to give you the initial concentration. All first-order reactants will obey this kind of behavior. So all those first-order reactions, if you plot the natural log of the reactant concentration versus time, you should get a straight line. And the straight line slope is related to K, and the straight line y-intercept is related to the amount you started with. So you can actually confirm or figure out how much you started with. You can get the rate constant K. Oh man, that's pretty cool. Second-order reactants can also be analyzed in this kind of function. You plot 1 over the concentration versus time. If you look at the handout, there's a kinetics handout in the companion or online. It will give you the exact values. I will mention them here a little bit in the future. But because first order is so common, that's why I want to really push this. Natural log of the reactant concentration versus time will give you a straight line. That's going to be related to the rate constant K and the amount of reactant you started with, and this is what linear regression is super useful for when it comes to chemistry. You plug kinetic data in, the linear regression gives you the slope and the y-intercept out, you are good to go. This picture right here, especially right here, shows the different kinds of rate orders. And we just went through the one that was the most common, which was the first order reactant. And if you go over there to the more right side, natural log of r versus time t is going to give you a straight line, slope equals negative k, etc., etc. Now, for zero order reactants, if you plotted the concentration versus time, you're going to get a straight line, slope equals negative k. On the other hand, for second order reactants, you have to plot, as I mentioned in the last slide, 1 over the concentration versus time. You will get a straight line. The slope equals positive k there. And again, all the y-intercepts are equal, or related to, to the R0, the amount of material you started with. You can also, again, see this kinetics cheat sheet, which is in the companion or online for better information about how these all work. The 3 graphs below were obtained for a chemical reaction, some given chemical reaction. And the question is, what is the order with respect to the rate law for this reaction? And you can see that there's an A versus time, a natural log of A versus time, and 1 over A versus time, all right? And the answer, the punchline to this question is going to be the one that gives you the straight line. So you can see that 1 over A versus time is giving you a straight line. The other ones did not. Well, if the 1 over A versus time is giving you the straight line, that's a test for a second order reaction. So anytime 1 over A versus time gives you the best straight line, that's going to be second order. If natural log of A versus time would have given you a best straight line, it would have been first order. And if A versus time was the straight line, it would have been zero order. One of those 3 should fit the reaction if you've done everything right, of course.